Namaste, welcome to the next video of Machine Learning Technique course. In this video, we'll implement naive-Bayes classifier from scratch. To begin with, we import a basic Python library which is NumPy for this implementation. Let's quickly recap what is naive-Bayes classifier. Naive-Bayes classifier is a generative classifier. It estimates probability of a sample belonging to a class using Bayes theorem. The posterior probability is calculated as prior into likelihood divided by evidence. Prior is P of y and likelihood P of x given y. And the posterior is P of y given x, which is the probability of a sample belonging to class y, and the evidence is P of x. It simplifies the calculation of likelihood with conditional independence assumption. Naive-Bayes classifier assumes that the features are conditionally independent given labels. And because of this conditional assumption, we can express the likelihood as, so the likelihood is P of x given y, where x is a vector. So we have P of x1, x2 all the way up to xm given y. These are m features. So this is the joint probability of features given the label. So now, because of the conditional independence assumption, we can write this joint probability as a product of individual conditional probabilities. So we can write this joint probability as P of x1 given y into P of x2 given y all the way up to P of xm given y. And we can write this compactly as a product of conditional probability of individual feature given the label, and we basically multiply all these conditional probabilities. Now we can substitute the likelihood in the Bayes theorem. So what happens is we want to, let's say, find out the posterior probability of a sample belonging to class yc. So this becomes the prior probability of yc into the conditional probability of each feature given label yc, and the product of that, which is what we got from this particular formula. We have substituted it over here. And evidence we basically calculate by summing up prior into likelihood for each and every class. So we are summing over each class label, the product of prior and the likelihood. So we perform this calculation of posterior probability in log space to avoid issues with underflow due to multiplication of small numbers. And we assign the class label that results in highest value of the numerator, that is the one that gets us the highest value of likelihood into prior. Now note that this evidence is fixed for all the labels, and this evidence mainly acts as a normalizing constant. So we assign the label y, that label y that results in the maximum value of the likelihood into the prior. And since we are performing this computation in log space, we are taking log, so we have log of py plus, so this product in log space becomes addition in the log space. So this is addition over m features log of p of xj given y. Now if we are interested in calculating the posterior probability, then we need to perform the full calculation of the Bayes formula. And the most time consuming part is to calculate the denominator. So let's see how to calculate this denominator. So far we have seen how to calculate the numerator in log space. So now what we do is we calculate the numerator for each and every class label in the log space, and then we convert this numerator from log space into probability by taking the exponential on both the sides. So when we take exponential on this side, exponential and log gets cancelled, and we get the joint probability of the features and the label, and that can be expressed as exponential of log of the joint probability. And this joint probability is nothing but, it can be expressed as likelihood into prior, so which is this particular which can be calculated with this particular formula. Now what we do is we basically sum up all these probabilities to get the evidence. So P of x is essentially sum over all the label, the joint probability of the features and the label. So we basically sum up the exponential of log of the joint probability over all labels to get the evidence. And then we substitute these values for the joint probability between the features and the label and the evidence, and that gives us the posterior probability. So naive Bayes classifier, as we said, is used in applications like document classification and spam filtering. So now what is the learning problem in naive Bayes classifier? So here, if you look at this particular formula, we do not know the values of PYC, which is the prior probability for each and every label. In addition to that, we also do not know the parameters of the conditional distribution of individual feature given the class label. So we have k prior probabilities for k classes, that is py1, py2 all the way up to pyk, and we have k into k times m class conditional probabilities, or km class conditional probabilities. For each label we have m features, so we need to estimate the class conditional probabilities for all features, all m features for each class, and since we have k classes, we have km class conditional probabilities to estimate. Now the class conditional probabilities or densities depend on the nature of the feature. So we have seen some of the popular class conditional densities that are used in naive Bayes classifier. So whenever the feature xj is a binary feature, we use Bernoulli distribution to model the class conditional density, that is P of xj given yc. If xj is a categorical feature, that is it takes more than two discrete values, then we use categorical distribution to model the class conditional density, that is P of xj given yc, where xj is a categorical feature. Then we have multinomial distribution. So when x is a count vector and the sum of all x represent the length of the object, then we use multinomial distribution to model the joint probability, the joint probability of the features given the label. And finally, if xj is a continuous feature, that is it takes a real value, then we use Gaussian or normal distribution to model the class conditional density. So we will implement these different class conditional densities in different naive Bayes implementation. We'll discuss the parameter estimation in detail in each of the implementation. So now what we'll do is we'll break the video into three different parts. So in this part we'll be covering Bernoulli distribution or Bernoulli naive Bayes. In the next video we'll cover Gaussian naive Bayes, and finally we'll cover multinomial naive Bayes. Let's study Bernoulli naive Bayes. So the important part is to perform parameter estimation, that is estimate the class conditional densities and the priors. Let's first study how to perform the class conditional density estimation. So we have parameter, that is w j by c. So this is the parameter corresponding to the jth feature for the class label yc. And how do we calculate this parameter, or how do you estimate this parameter? It is estimated as the sum over all the feature values of xj wherever we have a class label yc divided by the total number of examples with class label yc. In other words, we take average of feature value xj in examples with label yc. So you can see that this particular part, which is 1 of yi equal to yc, gets us examples with label yc, and then we sum up xj of I, where I is the index of the example. So we sum up xj across all examples with label yc, and we divide it by the total number of examples with label yc. Then the class prior is obtained as, so class prior is wyc. So this is the prior for class yc. It is obtained as the ratio of the total number of examples with label yc to the total number of examples in the training set. So numerator gives us the total number of examples with label yc, and we divide it by the total number of examples in the training set. So one of the things that we'll do in naive-Bayes classifier is that while estimating the parameters of the model, we'll process examples from each label separately and estimate the parameters. So here is the fit function. So we first find out a number of samples and number of features by accessing the shape of the feature matrix, and we have a label vector also as an argument. So from label vector we find out the total number of classes by performing np.unique on the label vector. So we have number of classes, we have number of samples and number of features, and then we use these quantities to initialize the weight vectors. So we have w that records the parameter of m different conditional densities, m different Bernoulli conditional densities, and we do it for k classes. So it has got total km values. These are km Bernoulli. These are km parameters of km Bernoulli distributions. And then we have k priors. So we initialize w and w priors, and then what we do is we process examples from each class separately. So we first get examples with label C. So we have a feature vector with examples exclusively from class C, and then we estimate w j by c, that is a parameter of Bernoulli distribution with class label yc and variable j. So here we have Bernoulli distribution, which is p of xj given yc is distributed according to Bernoulli distribution with parameter w j by c. So now what we'll do is we will perform a vectorized operation and we'll estimate all m parameters of m different Bernoulli distribution corresponding to each feature. So what we do is we calculate the summation of different features, and we divide that summation by the total number of examples in class C, and that's how we get the parameter vector W, which has got the parameter of m Bernoulli distribution for class C. And then we also estimate the prior probabilities, where we take a ratio of total number of examples with label C and the total number of examples in the training set. So this is how we get W and W priors. Let us look at the parameter estimation in step-by-step manner. So here what we have done is we have taken a feature matrix with shape 4, 2, and each so there are two features x1 and x2, and both of them are distributed according to Bernoulli distribution, of course, for each label. So we have 4 examples. Each example is represented with 2 features, and then we have a label vector with with 4 different components that are 4 labels, one corresponding to each label. So first and the last example comes from class 1, and the middle 2 examples come from class 0. Then we call the fit method with feature matrix and label vector as arguments, and it returns the parameters of Bernoulli distribution and prior. So we get a weight vector of 0, 1 and 1, 0, and we get a prior vector of 0.5 and 0.5. So now you can see that there are a few observations. There are 50% examples that are from class 1 and from class 0, hence the prior probability vector has 0.5 for each class. And note that for class 0, we have value of x1 equal to 0 and value of x2 is equal to 1. So that's why you see that W01 is 0 and W02 is 1, that you can see in this weight matrix. And for class 1 we have x1 equal to 1 and x2 equal to 0, and hence the parameter of Bernoulli distribution are 1 and 0. So let us perform this calculation step by step. So first we filter examples from a class, say class 1. So we have 2 examples, and those examples have 1 for feature x1 and 0 for feature x2. Now we perform the feature wise sum. So the sum of xc along the axis 0 is 2 and 0. So this is the column sum. We get values of 2 and 0, and we divide this sum by the class count. So here the count is 2, and hence we get a feature vector, a weight vector of 1 and 0 corresponding to class 1. So this process is also repeated for class 0, and we get a weight vector for class 0, and these weights corresponds to distribution of Bernoulli conditional distribution corresponding to each feature given the class label. Now you can see that there is a 0 in certain Bernoulli distribution have parameter 0, or the probability of generating, let's say, feature 2 for class 1, that probability is 0, and these 0 values could be problematic because it leads to 0 posterior probability. So we fix this problem with Laplace correction, or by adding a small dummy count in each class for each feature. So you can see that what we can do is we can calculate class prior with Laplace correction. So what we have done is we have retained the original formula, but in the numerator we have added alpha, and in the denominator we have added k times alpha, because there are k classes and for each class we have added alpha. So in order to compensate that, we have added k alpha in the denominator. We do the same thing with the class conditional density. We add alpha in the numerator and 2 alpha in the denominator. And why 2 alpha? Because there are 2 values, 0 and 1. So each feature is a binary in nature. That's why we add 2 alpha in the denominator. And remember, because we are using Laplace correction or smoothing, the value of alpha is equal to 1. As a next step, let us perform the inference where we'll assign a class label to each example. So remember that we assign class label that result in the largest product of likelihood and prior. So we assign the label YC that results in the highest sum in the log space of log likelihood and log of prior. So here the log of the likelihood, which is log of p xj given yc parameterized by w, we write this as w jyc raised to xj into 1 minus w jyc raised to 1 minus xj, and this comes because of the assumption of Bernoulli distribution. So now when we apply log on this, so this become xj log of wjyc plus 1 minus xj log of 1 minus wjyc. Now we can perform this calculation in the log space to avoid the problem of underflow. And we can vectorize also this particular operation with the following implementation. So we assign we get the label vector y corresponding to each example in the test set, and that is so we assign the label y such that we get the highest product or the largest product of likelihood and prior. So this particular calculation can be performed in vectorized form by taking a product of x and log of w transpose plus 1 minus x. This is another matrix, another feature matrix which is obtained by subtracting the feature matrix from 1 into log of 1 minus w transpose, and we add the log of w prior vector to this particular calculation, and we get the class label for each and every example in the test set. So we implement this in a class. So we have a Bernoulli naive Bayes class. We initialize in the constructor, we are setting the value of alpha to 1. Then we have a fit function, which is what we have implemented earlier, and we store the values of parameter as class member variables, and then we use these estimated parameters in calculating the log likelihood and prior product. This is the vectorized implementation that we just discussed. And there are two functions for prediction. One is a predict function that assigns the class label to each example, and then we also have a predict underscore proba function that calculates the probability for each example belonging to a class. And here we in both these cases we first calculate the product of so basically we calculate the log likelihood and prior product and use that for assigning the labels as well as to predict the probability of a sample belonging to a class. Now I'll give a short demonstration of this implementation in two setups. In the first setup is a binary setup and second is a multi-class classification setup, and you can see that the same implementation works both in case of binary as well as multi-class classification setup. So here we first instantiate an object of Bernoulli naive Bayes and we use it to estimate the parameter for the given feature vector and given feature matrix and the label vector. And remember, we have set this feature matrix over here. So we have feature matrix with shape 4, 2 with values 1, 0, 0, 1, 0, 1 and 1, 0 for 4 samples, and we have 4 samples with label 1, 0, 0 and 1. Now since we are using Laplace correction for estimation of the parameters, we do not get 0 here. Earlier we were getting 0, now we are getting 0.25 and 0.75 as the parameters of the Bernoulli distribution corresponding to class label 0, and for class label 1 we are getting the parameter of the first Bernoulli distribution is 0.75 and the second Bernoulli distribution is 0.25, and the priors are 0.5 and 0.5. We have 50% examples from class 0 and 50% examples from class 1. Now we predict classes for the input by calling the predict function on Bernoulli naive Bayes object and passing the feature matrix, and we get the labels of 1, 0, 0 and 1. So this is exactly what were the labels of each example. So they are matching perfectly. So one thing that I would like to note here is that the class labels are inferred by selecting the labels that result into the highest value of product of likelihood and prior. And here what we have done is we have printed the product of likelihood and prior in the log space. And you can see that for the first example, the product is, we get the higher value of product for class label 1, and hence we assign the class label 1 to the first example. For the second example, we get the highest value of the product of likelihood and prior for class 0, hence we assign the class 0. For the third example, again the same thing is observed, we assign it to class 0, and for the final example, the highest value of the product is for class label 1, and hence we assign the class label 1 to the last example. Now let us predict probabilities for each sample that we can do with predict_proba function that we calculate or that we call on the Bernoulli NB object. We pass the feature matrix to it, and you can see that the probabilities are, for the first example, the probability of belonging to class 0 is 0.1 and class 1 is 0.9. So obviously the first example is assigned to class 1. For the second example, the probability of belonging to class 0 is 0.9 and probability of belonging to class 1 is 0.1. Hence we assign the second and third example to class 0, and the fourth example is just like the first example, where the probability of this example belonging to class 0 is 0.1 and class 1 is 0.9, hence we assign the class 1 to the fourth example. So our naive-based implementation also works in multi-class settings. So here we have created a toy data set with 3 classes. So we have 6 examples in all, and we estimate the parameters of Bernoulli distribution and class priors. So we instantiate an object of Bernoulli naive-based classifier. We call the fit function by passing the feature matrix and label vector to it. You can see that all the 3 classes, there are 2 examples each, hence the prior probabilities are 0.33 each, and the class conditional densities are 0.25 and 0.75. Those are the parameters for the class 0, 0.75 and 0.25 for the class 1, and 0.75 and 0.75 for class 2. Let us predict classes for input example. So for that, we call the predict function on Bernoulli NB object by passing the feature matrix to it. And you can see that the first and the fourth example get class label 1, second and third example get class label 0, and the last 2 examples get class label 2. And we can also calculate the probability for each sample of belonging to different classes. And you can see that these probabilities row wise will sum up to 1. So the first example gets the probability of 0.69 of belonging to class 1. The fourth example also gets the probability of 0.69 of belonging to class 1, and so on. So here in the last 2 examples we get the probability of 0.6 of these 2 examples belonging to class 2. So in this video we implemented the Bernoulli NB classifier from scratch. In the next video we'll implement Gaussian NB classifier.